My name is Tiffany Ho, and I compiled this presentation to discuss key concepts of simple linear regression analysis. By the end of this presentation, you should have working knowledge of what simple linear regression is. First, I will provide a brief definition of simple linear regression and describe when it is used. Second, I discuss key assumptions and conditions. Third, I will explain how simple linear regression is different from correlation. Fourth, I will provide an example of simple linear regression to illustrate how this concept is used. Fifth and finally, I demonstrate how simple linear regression is generated in SPSS and explain how to interpret the results. Let's begin with the first item on our agenda. Simple linear regression is a method that allows us to study relationships between two continuous variables. Our text mentions that other terms referring to simple linear regression include simple regression and bivariate regression. Simple linear regression is used to make predictions of one variable given another variable. In simple regression, there is one independent variable and one dependent variable. The variable we are predicting is called the dependent variable and is referred to as y. The variable we are basing our predictions on is called the independent variable and is referred to as x. Simple linear regression can be used for prediction under certain conditions. First, there must be no more than two variables. Second, both variables must be continuous. Finally, variables should have a linear relationship, and they also should be normally distributed. If we were given a research question and corresponding variables, we can quickly determine if the variables meet the first two assumptions. But to determine if the variables meet the last two assumptions, we will have to conduct some initial analysis of the dataset, which I will discuss in more detail later in this presentation. You may be wondering, what is the difference between simple linear regression and correlation? Well, the difference between the two may appear subtle, but simple regression and correlation mean different things. As Altman and Krzyzewski note, in correlation, both variables are sampled randomly from a population. Using these samples, we can then ask and determine if there is a relationship between these two samples. In simple regression, we are given some variable, the independent variable, and from this variable we observe a corresponding variable, dependent variable. Let's take another closer look at this. With simple linear regression, once we have a set of given data points x and their observed data points y, we can plot them on our xy graph to observe patterns. On this particular graph, the data points seem to have a negative relationship because as the value for x increases, the y value decreases. If we were to draw a line that best fit to characterize the data set, we will see that it slopes downward from the top left to the bottom right of the graph. We call this line the regression line. The regression line is important because it helps us predict y given x. To predict y, the regression line is represented using an algebraic equation, y equals mx plus b, where m is the slope of the line and b is the y-intercept. We can use SPSS to help us determine the slope and y-intercept in this equation. Let's pretend that in the graph here, the equation for the regression line is y equals negative x plus 11. If we know that x equals 2, then using substitution and simple algebra, we can expect that y will equal 9. Here we use the regression line equation to help us predict y given x. Now let's take a look at another example. In a study by Yoon and her colleagues, they conducted a normal life test of lumen degradation for LED light bulbs. A small sample of light bulbs were placed under three different conditions. Some were exposed at 25 degrees Celsius, some at 70, and others at 90. Then the average lumen emittance for bulbs placed in each condition were plotted on an XY graph shown here. We see that lumen emittance for bulbs subject to the conditions are about the same prior to 2,000 hours of use. But after 2,000 hours, we see a sharper decline in lumen emittance for both bulbs exposed to 70 and 90 degrees Celsius than the bulbs exposed to 25 degrees Celsius. If we were to draw regression lines to characterize the pattern of data points, we will see that the line for bulbs subjected to 70 and 90 degrees is steeper than the line for bulbs subjected to 25 degrees. Although the data are not reported for bulbs exposed to 70 and 90 degrees Celsius past 7,000 hours of use, using our regression line, we can safely predict that if the bulbs were still running at 8,000 hours, they would be expected to emit about 16 lumens. Now, thus far in our presentation, I discussed items 1 through 4 on the agenda. Now I will use SPSS to demonstrate an application of simple linear regression. Using the HSB dataset, posted on the course Moodle page during the first week, I posed the following question. Can we predict students' math test achievement from their motivation? Before we begin performing functions within SPSS to answer this question, let's do a quick check to ensure that the question posed can be appropriately answered using simple regression. First, are there two variables? The answer is yes. These two variables are math test achievement and motivation. Now second, are the variables continuous? The answer is yes. If you look at the HSB dataset, you will see that both of these variables are marked scale. Next, do the variables have a linear relationship, and are the variables approximately normally distributed? Well, to answer these last two questions, we'll have to use SPSS to help us determine this. So to determine whether the assumption of linearity is fulfilled, I will generate a scatter plot. I go to my HSB data file, I select graphs, I go to legacy dialogues, then select scatter dot. A new dialog box appears, and I select simple scatter and then hit define to proceed. A new box appears. I place math achievement test variable in the y-axis box, and I place the motivation scale in the x-axis box. I also add a title to my scatter plot by selecting title. Then I generate my scatter plot. You will notice that in my scatter plot, I included a regression line to help me determine if there is, in fact, a linear relationship between the two variables. Based on the regression line, I can see that r squared is 0.1, which, according to Cohen's guidelines on page 102 of our text, there is approximately a medium effect size. This means the regression line somewhat fits the scatter plot well. We can say then that there is generally a linear relationship between the two variables. Now, coming back to our quick check questions, we can now say that yes, the variables, math test achievement and motivation, have a linear relationship. Now we have to explore the last quick check question. To do this, let's go back to the HSB data file. We have already learned that to determine if a variable is approximately normally distributed, we can check this by running descriptive statistics on the variable to determine its skewness statistic. To do this, we select Analyze, select Descriptive Statistics, then we select Descriptives. The Descriptives dialog box appears. In the Variables box, I insert Math Achievement Test and Motivation Scale, then I select Options. The Descriptives Options dialog box appears. I selected a few options to run, but most importantly, I selected the skewness option, as this is the information I'm most interested in. Based on the parameters established here, I run my descriptive statistics. My descriptive statistics shows me the skewness statistics for both of my variables, which is 0.044 for Math Achievement Test and negative 0.570 for Motivation Scale. Our text suggests that the skewness statistics for the variable should fall between negative and positive 1 for the data on the variable to be considered approximately normally distributed. Looking at what we have, I can say that these variables are within range for it to be considered approximately normally distributed. Finally, we can say that we determined that yes, the variables are approximately normally distributed. Now we know that our variables fulfill the assumptions. I am ready to use simple linear regression analysis to answer the question proposed. I go back to my HSB dataset. Within my dataset, I click on Analyze, Regression, and select Linear. The Linear Regression dialog box opens. I place Math Achievement Test in the Dependent Variable box and Motivation Scale in the Independent Variable box. With these parameters in place, I generate the following output in SPSS. Now my output file shows me a few things. The variables entered removed table shows me that I conducted simple linear regression using the enter method and entered motivation as the independent variable. The model summary table notes that R is 0.316, which is the bivariate between math test achievement and motivation, or the correlation between the variables. Now R squared is 0.1, meaning that motivation explains just about 10% of the variance observed in math test achievement. The ANOVA table provides information about the test of statistical significance of the linear regression. Here the significance value is 0.006. The coefficient table also provides us with additional information about the linear regression between math test achievement and motivation. The unstandardized coefficient 3.347, which is located next to the motivation, is the slope within the regression line, and the coefficient 2.982 next to constant is the y-intercept. The standardized coefficient, 0.316, represents the correlation between the two variables. You may recall this number is also reported in the model summary table in the previous slide. Now, to answer the question, can we predict students' math test achievement from their motivation, I conclude no, given the significance is 0.006 and I set alpha at 0.001. Also, please keep in mind that as previously calculated, R is 0.316, which according to Cohen's guidelines on page 102 of our text, this indicates only a moderate effect size, and R squared of 0.1 explains only 10% of the variance observed in math test achievement. Collectively, the various pieces of evidence I generated in my output files help me conclude that motivation is not a statistically significant predictor of math test achievement. But if I set my alpha at a different value, say 0.01, then I would draw a different conclusion. Thus far in this presentation, I discussed a few things. I talked about the definition of simple linear regression, its assumptions and conditions, and how it is different from correlation. I also presented an example of how simple linear regression is used, and I demonstrated by using a simple example in SPSS to show how to apply simple linear regression. These are the references I used in my presentation, and this concludes my presentation. I welcome any questions, comments, and feedback you may have about this presentation. Thank you so much for watching.